Welcome to The Explainer. Today we are diving into one of the biggest, most mind-bending ideas in all of physics. The idea that space-time itself, the fabric of our reality, isn't fundamental at all. It might just be an illusion, or maybe something that emerges from a much, much deeper reality.
So, how could a top physicist like Leonard Susskind say something that sounds like it's straight out of a movie? Well, to even begin to understand that, we first have to get our heads around the single deepest conflict in all of science. Okay, let's get into it. You see, for about 100 years now, our picture of the universe has been built on two incredible pillars. Two theories that work perfectly in their own domains. But when you try to put them together, they just fundamentally do not get along.
And this slide right here lays out the whole conflict perfectly. On one side, you've got Einstein's general relativity. It gives us this beautiful, smooth, predictable cosmos, where gravity is just the gentle curving of space-time. But on the other side, you have quantum mechanics, which runs the show in the bizarre, pixelated world of tiny particles, where nothing is certain and everything's a game of chance.
The real problem hits when their territories overlap. Think about the center of a black hole, or the very first instant of the Big Bang. You've got insane gravity in a tiny, tiny space. Both theories should apply here, but they give you completely different, totally contradictory answers. This breakdown is what's forced physicists to think way outside the box.
So what if the reason they don't fit is because we've got it all wrong? What if we're looking at this completely backwards? What if space-time isn't the fundamental stage of the universe, but is actually a collective effect, something that just arises from a deeper level of reality?
This idea is called emergence, and honestly, it's happening all around us. It's just how complex things, complex behaviors, can bubble up from very simple rules. And to get a feel for what that means, you don't have to look far. Just think about something as simple as temperature. So here's the crucial point. A single, solitary water molecule isn't hot or cold. It doesn't have a temperature. But get a whole bunch of them together, all jiggling around, and suddenly the property we call temperature emerges from their collective motion. It feels real, right? We can measure it, but it's not fundamental to any one particle. And this is the giant, mind-bending question at the heart of all this. Could space and time themselves be just like temperature, a collective property that emerges from a deeper reality that has no space and no time? A reality built from nothing but pure quantum information. So where did this wild idea even come from? Well, one of the first big clues came from studying the most extreme, most mysterious places in the universe we know of, black holes. And that line of thinking led to something called the Holographic Principle.
This idea, which came from people like Gerard Hooft and Leonard Susskind, popped out of a really weird puzzle with black holes. They found that all the information that falls into a black hole seems to get smeared out and stored on its two-dimensional surface, the event horizon, not its three-dimensional volume. It's a huge clue that our 3D reality might just be a projection of physics happening on some distant 2D surface.
And this gets really concrete with something called the AdS-CFT correspondence. That's a bit of a mouthful, but think of it like this. It's a mathematical dictionary that translates a complex world with gravity, like ours, into a simpler world without gravity that lives on its boundary. In this picture, space-time literally grows out of the quantum interactions that are happening on that boundary.
Okay, but the rabbit hole goes deeper. It's not just about holograms. The latest breakthroughs are pointing to something even stranger, that the very fabric of space-time is woven together by one of the weirdest features of quantum mechanics, entanglement.
Albert Einstein famously called it spooky action at a distance. He hated it. It seemed to break all the rules. But what if that spooky connection isn't just a weird quirk of the universe? What if it's the very thing that stitches our universe together?
So what is entanglement? Well, imagine you have two particles that are linked. You can pull them apart, send them to opposite sides of the galaxy, and the moment you measure a property of one, you instantly know the state of the other. Instantly. It's a connection that just ignores space and distance as we know it.
So how does that build space? Well, the idea is breathtakingly simple and incredibly profound. The geometry of space, how close things are to each other, might be a direct reflection of how entangled they are. The more entanglement between two quantum systems, the closer they are in the space that emerges. Less entanglement means they're farther apart.
As the physicist Mark van Ramsdonk puts it, if you could somehow snip the threads of entanglement connecting two regions of this quantum system, the corresponding places in spacetime would literally drift apart and tear away from each other. So entanglement isn't just something that happens in spacetime, it's the very glue that holds spacetime together.
There's this classic phrase in physics from John Wheeler, it from bit. The idea that physical reality, the it, comes from information, the bit. Well, the modern version is it from qubit. It's this radical idea that the bottom of everything, reality isn't made of matter or energy, but of pure quantum information. The physical world we see emerges from how these fundamental qubits are entangled.
And you know, this isn't just some fringe idea from one corner of physics. This theme that space-time emerges from quantum information keeps popping up again and again in totally different independent attempts to find a theory of quantum gravity. They're all pointing to the same conclusion.
I mean, just look at this. You've got string theory, loop quantum gravity, causal set theory. They all have different starting points, different fundamental ingredients, but they all end up at the same incredible destination. The smooth, continuous spacetime we live in is not where the story begins. It's the end result. And it gets even weirder. Some of these models predict that if you could zoom in way, way down to the smallest possible scales, our universe wouldn't even have 4 dimensions anymore. It would be a chaotic, fractal-like mess that looks more like it has 2 dimensions. Our familiar 4-dimensional world is itself an emergent property that only shows up at large scales.
Okay, this is all pretty mind-bending stuff, but why does it actually matter? Well, it's because if spacetime is emergent, it changes everything. The whole hunt for a final theory of physics gets turned on its head. The secret to understanding gravity might not be about looking at bigger things, but about understanding the rules of quantum information and entanglement.
We don't have the final answer. Not yet. But all the clues are pointing in one direction, that the solid, continuous reality we experience is just a low-resolution snapshot of a much deeper quantum world. The universe we see might not be the real thing at all, but a beautiful, complex hologram projected from a hidden realm made of pure information. And if that's true, well, that changes everything.